Well, today we read the article Galois cohomology of weight vectors of algebraic integer by Lars Hessel. So let K be a complete discrete valuation field of characteristic 0 with residue field characteristic P bigger than 0. Let L over K be a finite Galois extension with a Galois group G, and suppose that the induced extension residue field is separable by the normal basis theorem, which is stated here. If L over K is a finite Galois extension with Galois group G, then there is some element of L such that L as a K vector space is the sum of K multiplied by element acting all the element of G sigma on this theta. So by this normal basis theorem, you see L is a projective Kg module, while as clear, L is a free key module, so it's a projective key module. There is a Galois action, but actually I do not know when you write this, do you mean a group algebra or? Yes, should be a group algebra, yes. Projective Kg module. Okay. So why he write this? It's because, let's recall, under some cases, to compute Hi, G, for example, M, under good condition, for example, if M is discrete and G is discrete for safety, it is the same as you computing the derived cohomology of the home factor. I think it's like, yes, like this. This Hi is the same as this derived factor, so you do compute Hi gem is the same as extra I as G module. Okay. Well, in the same way, I'm feeling that you can also compute this. Since the fixing point of M under the action of G is the same as homomorphism of the Kg module from K. So you say if for example here we put L, so if your L is a projective Kg module, okay, then what? This is the exact factor. No, sorry. Well, actually, this is not enough to conclude that if it's a projective Kg module, then its Galois group vanish, which is the purpose of the author when he say like this. He say like this. He said that L is always a projective Kg module, so there is no problem to compute the Galois cohomology of L. But the ring of integer OL is a projective OKG module under condition that L over K is terminally ramified. So when it's terminally ramified, you can still compute the Galois cohomology of OL, which is vanishing. But if it's not terminally ramified, you have to talk more. But still, we don't know why if the Galois module is a projective Kg module, then its Galois cohomology vanish. But we have some light on, for example, this article is a Galois module structure of cohomology group for terminally ramified covariant algebraic varieties. Well, this let's read this abstract. Let f(x) to y be a terminally ramified finite Galois covariant of projective varieties over a field P. Let F be a coherent G sheaf on X concerning the Kg module structure of the cohomology group. So the cohomology group already have a Kg module structure. This is probably another article, I think, by Nakajima. Not Nakajima, yes, still by him. So it's this article, the first article, I guess. Invention. It said that K be a field and F from X to Y of finite detail Galois current projective right over K. For coherent sheaf F on Y is a group Gal X over Y. Naturally, X on the sheaf, and hence the cohomology group is a Kg module. We shall investigate the Kg module structure of this HI. Our general result is, with the same notation as above, there exists a finite complex of Kg modules with the following property. Each Li is a finitely generated free Kg module. The ith cohomology group of the complex L is isomorphic to Hi as a Kg module. You see? Li is a finitely generated free Kg module. The ith cohomology group of the complex L is isomorphic to the cohomology group Hi as Kg module. And the second theorem says, assume Hi is 0 for our index I except for one value of I. So I equals n, then this Hn is a free Kg. Well, let's back to our article here. Here what they said. Concerning the Kg module structure of the Galois group, of the cohomology group, we first give a result for x and y of arbitrary dimension. Show that in particular Hn is Kg projective when Hi equals 0. Next, we further assume that xy are non-singular curve and f locally free. In this case, the exact relation is given between the Kg module and H1. This is the introduction. K be field and fx to y of finite Galois curving of projective right x and y over K. We put Galois group and consider the coherent G sheaf f on x. Here G sheaf means a sheaf on which G acts compatibly with its action on x. The group G naturally acts on the cohomology group Hi, and concerning the Kg module structure of Hi, which we did the case where f is unramified and give a relation among the Kg modules in a similar sense as the Riemann-Roch theorem gives the relation dimension Hi. As a special case, we prove that Hn is Kg free if Hi equals 0. This paper considers the case where f is stably ramified. The result is given for xy of arbitrary dimension. These two call the addition xf is Kg projective. Which I xf is 0. So I not 0. Well, actually, we are stupid on those things. It's something very basic. We just slowly go through this part, basic knowledge, induce a co-induced module. Then we will say why the module is a projective Kg module implies Galois cohomology vanish. Okay, so induced and co-induced module, we remark that if we have a morphism f from H to G of topological group, then there exists a factor given by where f star A is equal to A as subgroup and the H structure is obtained through F. So you start from G module. You got the H module through this F, denoted star A. It's like a pullback. If small a is inside star A and G and H, then it's just through F, okay? It's easy to see that it is a functor. Sometimes when it is clear what we mean by the context, we will write simply A instead of F star A. It is clear that F star is exact. Now we also remark that for any morphism of groups, small f from H to G with each and the discrete groups, for finite groups, we also construct a functor. Definition: let H and G be discrete or finite groups. For any morphism from H to G of topological groups, and for any H module M. Any H module M. We define a co-induced module. Define like this to make it into a G module. Actually, we see start from G module just by pullback F. We got a H module, but if you got a H module, how can you get a G module? I define a co-induced F on the module M to be the element of the homomorphism from G to M. Start with H module M. Define module to be or the homomorphism as topological group from G to M such that FHG is HFG. Well, here is a miss of notation. So there is some typo. So this module is defined to be the, actually this is a module. The element of this module are denoted by phi. We define to be those continuous homomorphism and topological group from G to M such that it's acting on element of H multiply G, we remove H out, staying G, and G acts on the element over here by this way, so it is a G module. So we have to check it is a G module. So G, we do not use G, let's use the A, okay? A phi, we have to check it satisfies the condition acting on HG. It should be phi acting on HJA. So A is inside G. We want to prove it's G module. So this is in G again. So by our definition of phi, it is phi it's just you removing H out, staying phi GA, and it's equal H acting on A phi J. Okay, so you see, take element phi from this module, this G phi is still in this module. It is G module. And obviously it's has a summation addition structure, making it a group. In the profinite case, the fact that the action is continuous follows from the fact that in the profinite case, the fact that the action is continuous follows from the fact that for any fine this homomorphism topology group GM, the stabilizer of phi contains an open normal subgroup. Yes, we know this action is continuous if and only if the stabilizer of phi contains an open normal subgroup. If GH are discrete, then this co-induced mode, by our definition here, is nothing but it's just telling you that you see, telling me that you are H linear. Okay, you're H linear. Anymorphism from the G to M, you're H linear. If M is injection, so H is just a subgroup of G, then denote them by this. If H is a trivial group, we will speak of co-induced module. You see, if H is trivial group, then this is what? This is nothing. This condition is nothing here. If G is trivial, we obtain the functor fixing by H. So you see the co-induced module as a set is nothing but the homomorphism from G to M. Because H is trivial, there is no restriction on the condition here. But as a module, you look at action on it in this way. This is the co-induced module. But if G is trivial, so here homomorphism from G to M is just one element to M, so you can map it to any element of M, satisfying this condition. And the action on phi is a trivial action, so there's nothing there. You see, if G is trivial, there's only one point. Since both are discrete, I think we're in the case discrete, yes, or profinite. To make it a continuous map, you can map it to any element, okay? Just to make sure you're fixed by H, so it's the same as this. The interesting case is when F is an injection. In this case, for discrete groups, we mark that ZG is free as ZH module over ZH. Let F from H to G be a morphism topology group with H and G discrete or profinite. When G module M and any H module N we have, this is the co-induced module we just constructed. We start from H module N, we make it a G module by our co-induced module. We claim that as a set, this is the same as the homomorphism as H module, bring back M, and on n. If H is a topological subgroup of G, the functor is exact. Well, this functor is exact, you see. If H is a topological subgroup of G, then the functor is exact. Co-induced GH sends injective objects, injective objects. Actually, if you want to compute cohomology group of this functor, you start with injective resolution. So you see, home M, this is composition, right? So in the case H is topological subgroup of G, this is exact, this is left exact, so it's left exact. Start with injective resolution of some here, for example n, you take injective resolution of n, and this sends injective object to injective object, and it's exact, so it sends injective resolution to injective resolution. Yes. Let's say this Shapiro's lemma. At HJB2 discrete or profinite groups with H topological subgroup of G, then there is isomorphism of factors. Let's say, so as we just said, we start from, for example, right hand side to compute this HIH, for example, and what you have to do, start with injective resolution. They're applying this fixed functor of H on it. Then you compute the ice cohomology of this. And then we look at the left hand side. What do? We still start with the injective resolution of M, as we remarked. Co-induced is the exact functor, and this is injective to the injective. So we got another injective resolution for this module. Then what you do, you compute the fixing point of G acting on this resolution. And you compute the ice cohomology. The problem for us is, what is this? Indeed. So the fixing point of G are elements of as definition. We first say, what is this module? This module is those satisfies for any element H, just moving H out. Moreover, if you're fixing by G, remember the action on it is given by G acting on map F. This is the morphism, this is the function acting this way. This is the G module structure on this induced module. If it's trivial, what does it mean? It means that this is equal to fx for any x and g. Well, this is interesting. This means that f is constant. Okay, f acting on g is a constant of m. But which elements of m? Indeed, the requirement is here. It is those elements. So here are all constant. So those constant C of M such that fixing by H. So you see, this is exactly the fixing point of H of M. So this is just Chan. Similar thing happened here. This is our proposition. Okay. Remark that any G module M can be embedded in co-induced module. What is good about this lemma? This lemma tells you how to realize a group cohomology of a group cohomology with bigger group, or you say how to realize some group cohomology of G into a group cohomology of a subgroup. Let H be a closed subgroup of discrete or profinite group G given by a morphism F. Let M be a co-induced G module. Then the pullback of M is an H co-induced module. If G and H are discrete, we have also another functor. Let's now in another direction. From H to G, a morphism discrete group, we define induced module this way. So A is H module. By doing this, we got a G module. This obvious left G action. Okay, the G action on it. If F is inclusion, we will write this. If H is a trivial group, we will speak of induced module. If H is a trivial group, this is morphism of group, okay? And F, H, G be morphism discrete group for any G module and any H module we have. Okay, again something similar. If F is inclusion and H has the induced order, then the functor is exact, that's the projective. It is sufficient to consider they can in fact play the role of injective module. Now we come back to our previous question. It's exactly what's written here. Our key is a Galois extension of fields for all q in zeta. Of course, we suppose it's a finite Galois extension, so this is a finite group. Then the Galois cohomology of the group cohomology of this Galois group vanish for any q in Z. This is a Tet cohomology, okay? This is what we claimed. It's the same claim because L is a direct summand of the SK vector space, which is the same as this tensor product. In this way, this is exactly the definition of an induced module. So it vanishes. This is not directly. What is more directly is by Shapiro's lemma. When you are induced module, your homology with positive index, your positive homological group or vanish, or you don't know the cohomology group vanish. The cohomology group vanish when you are co-induced module. But actually in the finite group case, the co-induced module and the induced module are isomorphic, so both vanish. So this is very obvious. You can easily construct the isomorphism. And this is the general form of the induced form, which is say have a building G module. Do like this. This is induced G module. Okay, it's like this. X is just Z module. It's the same thing as what we said. It is an induced G module if it's isomorphic as module to this for some abelian group, or equivalently like this. This is our case. In our case, this is our G, and this field key is our abelian group. To see more precise, we reference to the book Cohomology of Number Fields, Newcrich, and other authors, which states like this. First they say it is a cyclic G module is just this vanish of the cohomology group when its degree is bigger than 0. It's called cohomologically trivial, or flasque in French, if for all n bigger than 0. For all closed subgroup, still vanish. Important example of cohomology trivial G modules are induced G module. You see here his definition of induced is a little different from us. This is the definition of our co-induced actually. But anyway, we have an isomorphism when G is finite group given by element here is topological continuous map from G to A such that, okay, so any element here we're sending it to the tensor product. Here is the group ring. As we saw, this is our definition of co-induced module, the cohomologically trivial. Yes, because when G is finite, it's isomorphic to our induced modules. Also, when n is minus, it's negative. This is the positive homological group, will vanish, and with the all vanish. So we can conclude. So now we come back to our very beginning. This article, Galois cohomology with vector of algebraic integers. So the introduction said, Well, by the normal basis theorem, L is always a projective Kg module. That's what we saw here. So it's a induced G module. So since G is a finite group, which is isomorphic to the co-induced G module, so the cohomology group will vanish. Okay, star implies for positive. But the ring of integer OL is a projective OKG module finally if L is temporally ramified. Okay, so this means what? It's L over K stably ramified. Galois group of this field extension on OL. Okay, but it's not good to say this vanish equivalent. At least we know this is true. When it's temporally ramified, the OL is again a co-induced module. Okay, I don't know actually why he will say this is projective KG mode, why this is important, but we have our proof. Just using this is a induced module. Okay, so this is okay if projective OKG module implies it is an induced module, or if this tells you the similar result like this theorem, then it's okay. But anyway, we go on. For wildly ramified extension, the structure of OL and the OKG module is very complicated and quite far from understood. We propose the ring of weight vector, which is more well-behaved object. Indeed, we show that for large class of extension, the probability group is 0. We conjecture that this is true in general. We recall that the ramification group defined finite filtration. Yes? This is our ramification group. Yes, no problem. Actually, as we know, for any finite separable extension over K, you can always put it into 3 parts. The first part is unramified, whose Galois group corresponds to G minus 1 over G0. The second part is temporally ramified, whose dimension of extension is coprime to P, and is the biggest factor of the dimension of L over L0, that is coprime to P. In other words, the left part, L over LT, is just the P power, and it's called wild ramification. The quotient G over G0 is canonically isomorphic to the Galois group of extension residue field. This is what we know because it's not ramified. You can use Hensel lemma to lift any automorphism of the residue field to the ring of integer level. The quotient G0 over G1 is cyclic for order prime to P. Yes, prime to P, because, and here you see you got more, you know it's cyclic. And the left parts are all p groups, abelian p groups. Hence, it suffices to show this is zero. Why he say it's sufficient to show this is zero when it's a totally ramified cyclic extension of order p? Because you see, he separated into three parts. For this part, unramified extension, it means OL over OK is trivial. OL is OK, the uniformizer is the same. It's trivial cohomology group, obviously. For this part is teamly ramified as he claimed. Teamly ramified case, the OL is a projective OKG module, which we guess is the same thing as this theorem stated here to make it into induced module, which implies the triviality of the cohomological group and also homological group thanks to the finite of the group G. So what is the left part is only this part means a wild ramification extension. But this wild ramification extension is an abelian P group. So you can, I think by the primary decomposition theorem, you write it as the direct sum of cyclic group, of course, of order P power. Okay, but if you work carefully with the P group, you should be able to realize it in steps of extension of order P. That's why we said like this. And how to put together those triviality of each part into triviality of the whole Galois group, I think it's okay by spectral sequence, by Hochschild spectral sequence, which tells you that okay, if H is subgroup of G, then let's not use H, let's use gamma. Sorry, let me rewrite it. So if gamma is a subgroup, then we relate the cohomology of the quotient with the cohomology of itself. So here is P plus Q. Yes, let's take a look into the original. Yes, Hochschild spectral sequence. A GB for finite group H, a closed normal subgroup of A of H, and A is a G module. Then there is this first quadrant spectral sequence, the quotient of the group G, the subgroup H, which convergent to the HP plus Q. So in particular, if this vanish for any Q, in particular for H0, then it means HP, this quotient group, zero converge to HP, the whole group. Okay, so this will be a subgroup of G. If this subgroup is zero, then the cohomology of the whole group will rely on its quotient, which is isomorphic to this part. Okay, and you do the same. Actually, I'm feeling that if you use spectral sequence, this is more easier than we expected, because surely you are closed normal subgroup of G. Thus you have finite extension just. So once we can prove that for this gamma, for gamma this vanish, then for all it vanish. Okay, I think this looks okay if I didn't make some stupid mistake. So we focus on this. What's happened later is to prove this mean theorem of this article, that L will give you a totally ramified cyclic extension of order P. Suppose that T is bigger than some index. Then this is his restriction. It's not considering any filtrations. Okay, so some filtration, some extension. Then the probability group H0. This is what he will prove.